This is Neil Patwari. This segment is on binary FSK and specifically the coherent receiver. Remember, in binary FSK and in M-ary FSK in general, we form waveforms phi0 of t and phi1 of t. And if we had more than binary FSK, we would go all the way up to capital M minus 1. But for binary FSK, we're going to have two orthogonal waveforms. And these orthogonal waveforms are the cosines. So first of all, we're going to normalize so that we have unit energy. And this is the cosine at some frequency omega naught t multiplied by a pulse shape. And the other waveform is just going to be the cosine at a different frequency. We've talked about what that frequency needs to be, that it needs to be separated by an integer multiple of 1 over 2 times the symbol period. And those are our orthogonal waveforms. For the coherent receiver, we're going to correlate with each of these waveforms in order to find the symbols that we're sending. The symbols that we're sending, we have two of them. They're going to be, this one is A1, A0. The two different symbols are both a distance from the origin. So this one would be a comma 0 in the vector form. This one would be 0 comma a. So these vectors are our symbols, and they're essentially just a multiple of phi0 of t for a0 and a multiple of phi1 of t for a1. We're not doing a linear combination of our waveforms in FSK. So in our coherent receiver, what we do is we correlate, we multiply by the cosine, we run it through our matched filter p of t, or the time reversed version of p of t, and then we sample it at the end of the symbol, the end of every symbol. And from this sample, we get R0 and R1. These are our two dimensions. This will be R0, R1 vector. And the map filter, the optimal decision is to pick the symbol that this R0, R1 vector is closer to, either A0 or A1. That's our decision, which one is closer, and then we make our symbol decision. So the question in this segment is, what is the probability of error when we build this receiver? So to figure that out, we're going to do the steps that we typically do. We calculate the energy per symbol, and here one symbol is 1 bit because it's a binary FSK system. So we have the energy per symbol is the energy per bit. This is the average of the energies in each symbol. Each symbol is exactly a from the origin, so we just take a squared as its energy. And each of the two symbols is a squared in energy. So we get a squared. Okay, very simple. And this system is a system at which we have a distance between symbols of this d01. This d01 is this hypotenuse of a triangle with equal length, so it's a times square root of 2. And as we've shown, when you have this decision between two symbols and you calculate the probability of error, you get a Q function. And here I'm just using probability of error because the probability of bit error and the probability of symbol error are exactly the same thing. So I don't need to specify that it's bit error or symbol error. I'm going to get the Q function. Our original formula was that we take the distance, square it, and divide by 2n0. And so when I do that in this case, I get the Q function of a squared times 2 divided by 2n0, or a squared divided by n0. But a squared is also the energy per bit, so I'm going to use that and just write energy per bit divided by n naught. This is their function of the probability of error versus the EB over n naught. And that's all I have to do here. This is the probability of bit error and probability of symbol error in coherent reception for binary FSK. Next segment, we'll talk about when we use a non-coherent receiver and what that means.